The modern world is powered by electrical circuitry on a chip, the semiconductor chip underpinning computers, cell phones, the internet, and other applications. In the year 2025, humans are expected to be creating 175 zettabytes, that is 175 trillion gigabytes of new data. How can we ensure the security of sensitive data at such a high volume? And how can we address grand challenge like problems from privacy and security to climate change, leveraging this data, especially given the limited capability of current computers? A promising alternative is emerging quantum communication and computation technologies. For this to happen, however, it will require the widespread development of powerful new quantum optical circuits that are capable of securely processing the massive amounts of information we generate every day. Researchers in USC's Mork Family Department of Chemical Engineering and Materials Science have made a breakthrough to help enable this technology. While a traditional electrical circuit is a pathway along which electrons from an electric charge flow, a quantum optical circuit uses light sources that generate individual light particles or photons on demand, one at a time, acting as information carrying bits, quantum bits or qubits. These light sources are nano-sized semiconductor quantum dots, tiny manufactured collections of tens of thousands to a million atoms packed within a volume of linear size less than a thousandth of the thickness of typical human hair buried in a matrix of another suitable semiconductor. They have so far been proven to be the most versatile on-demand single photon generators. The optical circuit requires these single photon sources to be arranged on a semiconductor chip in a regular pattern. Photons with nearly identical wavelength from the sources must then be released in a guided direction. This allows them to be manipulated to form interactions with other photons and particles to transmit and process information. Until now, there has been a significant barrier to the development of such circuits. For example, in current manufacturing techniques, quantum dots have different sizes and shapes and assemble on the chip in random locations. The fact that the dots have different sizes and shapes mean that the photons they release do not have uniform wavelengths. This and the lack of positional order make them unsuitable for use in the development of optical circuits. In recently published work, researchers at USC have shown that single photons can indeed be emitted in a uniform way from quantum dots arranged in a precise pattern. It should be noted that the method of aligning quantum dots was first developed at USC nearly 30 years ago, well before the current explosive research activity in quantum information and interest in on-chip single photon sources. In this latest work, the USC team has used such methods to create single quantum dots with their remarkable single photon emission characteristics. It is expected that the ability to precisely align uniformly emitting quantum dots will enable the production of optical circuits, potentially leading to novel advancements in quantum computing and communications technologies. The work is published in the journal APL Photonics. The breakthrough paves the way to the next steps required to move from lab demonstration of single photon physics to chip scale fabrication of quantum photonic circuits. This has potential applications in quantum communication, imaging, sensing, and quantum simulations and computation. It is essential that quantum dots be ordered in a precise way so that photons released from any two or more dots can be manipulated to connect with each other on the chip. This will form the basis of building unit for quantum optical circuits. If the source where the photons come from is randomly located, this can be made to happen. The current technology that is allowing us to communicate online, for instance using a technological platform such as Zoom, is based on the silicon integrated electronic chip. If the transistors on that chip are not placed in exact designed locations, there would be no integrated electrical circuit. It is the same requirement for photon sources such as quantum dots to create quantum optical circuits.